Hi, and welcome to your first lesson in thermal energy. At the end of this lesson, you should be able to distinguish between temperature and heat, and understand the direction in which heat flows in real-life applications. We will also be doing some calculations using this formula here, as well as variations of that calculation. After this lesson, you will be viewing a demonstration of an experiment and plotting a graph similar to the one that we will be discussing in this lesson. So I hope you enjoy this lesson, and if there's any questions you have during or after the lesson, feel free to contact me. So let's get started. So let's start with looking at the differences between heat and temperature. Heat is a transfer or a flow of thermal energy from one object to another, or the flow can be from a system to its surroundings, or from the surroundings into the system as well. The flow of the thermal energy starts from places or objects with a higher temperature, and the heat moves to places of lower temperature. Heat is measured in joules. So heat here is your quantity that we could measure, and the unit that it is measured in is joules. So let's take a look at these three scenarios. We have heat being moved from one object to another. So suppose we had one object here, so that's my object 1, and I have another object that's touching that object, that's 2, and this one here is hot, and this one here is colder. What we are saying is that the heat or the thermal energy is going to move from the hot object to the colder object. So it will move that way. The heat will move that way, from the hot to the cold. And this is when we have two bodies. Okay, one object to another. The second scenario is from a system to its surroundings. So suppose we had a system here, maybe a hot motor or a hot cup of tea, and this is hot. And then we have the surroundings, and the surroundings is your atmosphere, the air around in your room, right? So your surroundings. And this here is colder than your system or your object. The flow of the thermal energy or the heat will move from the hot object to the colder room. Alright, so it will move outwards from the hot to areas that is colder. The third scenario is when we have heat moving from the surroundings into the system. So for example, we have a block of ice sitting on your counter on a table, and the ice is cold, and your surroundings is actually hotter, right? So hot air in your surroundings. The direction that the heat would move would be from the hot air into the system. Alright, so from your surroundings into the system. And what will happen here? Your ice will start to melt. Okay, so these are three scenarios: from one body to a next, one object to a next, from a system or body to the surroundings, and or from the surroundings to a system. Of course, the most important thing is it moves from a higher temperature to a lower temperature. Okay. Now, when heat energy is absorbed by an object, for example, in example 3 here, it makes it hotter. And when it is lost by an object, it leaves it colder. For example, when a block of ice is placed on a kitchen counter, it absorbs the heat energy from its surroundings and melts, right? That's what we talk about here. And when the water is placed in the freezer, it loses energy to the surroundings in the freezer and becomes ice. So you could draw a little illustration. You have your table, and then you have your block of ice on your table, and you draw your heat from the surroundings moving into the block of ice. So heat here is being absorbed by the ice. Okay, your surroundings here is hotter, and then your ice is going to absorb that heat and start to melt. That's this scenario here. And then the second scenario here is when the water is placed in the freezer. So you have your freezer and you fill your ice tray with water. What is happening here is that heat will be lost. It will lose heat to the surroundings in the freezer, and the water will turn to ice. Okay, so the heat will come out of the water. Now when we use words such as hot and cold, warm, tepid, or cool, it tells us about the hotness or the temperature of an object. However, these words are not precise, since what may be warm to you might be cold for another person. When we need to be exact about the temperature of an object, we use instruments to measure temperature, with graduations called degrees. A little later on in the lesson, we will talk about measuring temperature and the instruments we use to measure temperature, and we will look at the graduations and the units of temperature. An example of this here is having a fever. So you have a fever, but you feel cold and you're shivering, but at the same time your skin feels warm. You go to the doctor. To confirm that you have a fever, the doctor will use a thermometer to check your temperature, and this will accurately tell us if you have a fever or not according to your temperature that the doctor measured. So the words such as cold and warm and hot are not precise words that we want to use to describe heat. Now heat and temperature are not the same, so you need to remember this, okay? Heat and temperature are not the same. Heat is a form of energy. Temperature is a measure of how concentrated that energy is in an object. Heat tells us about the total energy in an object. Temperature tells us about the kinetic energy of the individual particles in that object. So heat here tells us about the total energy, and temperature tells us about the kinetic energy of the individual particles in that object. Now an example to show this would be a bath of cool water. So you have a bathtub. Hopefully this looks like a bathtub here, right? And your water in here is 27 degrees Celsius. So it's a warm bath. This is almost like room temperature. Okay, now the water in this bathtub, the mass of this water is more than the mass of the water in a mug. Okay, so a mug with boiling water. So the temperature in this mug here of the boiling water would be 100 degrees Celsius, because water boils at 100 degrees Celsius, and you would have your steam coming out of there. Now what we are seeing is that the heat is much less in the mug than the cool bath. There are fewer molecules in the mug. If I were to take this small mug of boiling water and throw it into this bathtub here, the water temperature would not change very much. Right? But if I were to take this tub of water and somehow throw it into this cup, the contents of the mug will become cooler. So the cool water has a lot more heat energy and a lower temperature than the mug of boiling water, okay, because of its mass. So the mass or the amount of the substance is very important too when determining heat and thermal energy. Temperature can tell us which way the thermal energy is being transferred. When thermal energy is transferred to an object, its temperature increases. When thermal energy is transferred away from an object, its temperature decreases. Okay, so the temperature of the system or the body or the object or the surroundings is important to know so that we could tell which way the thermal energy is going to be transferred. Because we said earlier that heat energy, thermal energy, moves from areas that are higher in temperature to areas that are lower in temperature. So now let's look at some real-life examples on page 2. So example 1. If you leave a hot drink on the table and wait for a while, does the drink heat up or cool off? Sounds like a trick question, right? You could probably give your friends this question and see what they come up with. So here we have a table. This is my table. And I have a mug on the table. And my mug has a hot drink in it. So here is hot. Okay. Now, if here is hot, my surroundings would be colder. So let's pretend this is a mug. And my mug is hot at 80 degrees Celsius. And my surroundings, which is the air, okay, so the air in my surroundings is at 28 degrees Celsius, which is normal room temperature for our climate. What do you think will happen? In what direction would the heat flow? Well, we know that it would move from the hotter object to the area of lower temperature. So it will move out into the air in the surroundings, or if the table is colder, it will move to the table. So heat is transferred out of the cup or the mug. Now, if heat is leaving or is removed from the hot object, then the drink inside your cup would cool off. Okay? Now example 2. If we leave a cold drink instead on the table and wait for a while, what will happen? So here I have my table again and my mug. Don't laugh at my drawing. Okay, and this is a cold drink, and this cold drink is at 10 degrees Celsius, and I have the same surroundings. The air in my surroundings is at 28 degrees Celsius. What will happen to the drink in the mug? Will it heat up or will it cool off? Well, heat would move from the hotter air into the colder mug. If the table is 28 degrees as well, the heat would move into the cup, which will heat up my drink. Let's look at the example 3. You are holding an ice cream cone in room temperature air. So my room temperature air here is going to be 25 degrees Celsius. Okay. How does heat flow between the ice cream, your hand, and the air? Now, normal body temperature is 37 degrees Celsius. Okay. Anything higher than 37 degrees Celsius, it means you have a fever. Now, what is the temperature of the ice cream? Well, the ice cream would be 0 degrees Celsius. It's cold. Okay, it's frozen. And it's mostly made up of frozen water with some flavoring and some milk in there, right? So, which way would our heat flow? Our heat would move from the area of higher temperature, which is my hand, into the ice cream, from the cone to the ice cream, okay? And the hot air in the room will move to the ice cream. Heat will also leave your hand and go into the air because my hand is hotter than the temperature in the room. So we have hand and we have the ice cream. We have the hand again and the air, and we have the air to the ice cream. Alright, I'm just putting this in some colors for you. So the heat moved from the hand to the ice cream, from the hand to the air, and air to the ice cream. So be sure to pause the video and take down all these extra notes, okay? Now example 4. Water is boiled on the stove in a teapot. How does heat flow in this picture? Well, we have a flame here, and this flame is at 1000 degrees Celsius. I have my water here, which is boiling 100 degrees Celsius because water boils at 100 degrees Celsius. The air in my room is 25 degrees Celsius. How does heat flow? Well, it will move from the areas that are hotter to areas that are lower in temperature. It will move from the flame to the pot, and then the heat of the pot to the air in the room. The temperature of the pot and the water inside is higher than the air in the room. Now, if steam decides to leave through that opening there, this is another way that heat would leave. Okay, so heat are going to leave through all these pathways here. Heat is not going to flow from the air into the pot because the air in the room is of a lower temperature than the pot, okay, and the water in the pot. And we also have the heat from the flame moving to the air as well. Now let's write down the scenarios that is happening here. We have heat flowing from the flame to the air, from the flame to the pot, then the pot to the water, and then to the air. We have the, right, so that's this one here, right? So from the water to the air through this opening here. And then we have from the pot to the air, and we have from the water to the air. Okay, so this one here is a complete pathway from the flame to the pot. The pot will heat up, the water will heat up inside, and then the pot will give off heat to the air, or it will give off, the water itself will give off heat through the opening here as steam. Okay, and these are all your heat flows. Okay, so on each of these arrows, write the word heat. Now let's look at example 5. You are holding two ice cream cones together. They are both at exactly 0 degrees Celsius. Does any thermal energy flow between the two ice cream scoops? So here I have my 0 degrees Celsius ice cream and my 0 degrees Celsius ice cream. So because there are no temperature difference between the two ice creams, there will be no thermal energy flow. So what's important here to note is that for heat to flow, there must be a temperature difference. Okay, there must be a temperature difference for heat to flow. So there's no flow of heat between the two ice cream cones. Now let's turn the page and take a look at example 6 and 7. A hot cup of chocolate is in your hands and you really want to drink it now, but it's too hot. How might you cool it without using ice or a refrigerator? So my first scenario that I remember doing is having a container with water. And this could be cold water or room temperature water. But the water must be at a lower temperature than the mug or the cup of hot chocolate tea. Okay, so this is my cup in my water. So our first scenario is to put mug or cup in water bath. So we make a little bath for a hot cup of tea. And which way would the heat flow? Well, the heat would flow from the hot tea to the mug to the water. We also have heat flowing from the hot tea to the air. Okay, so it goes to the air, or it goes into the water. So our heat flow here is from the tea to the mug or the cup and into the water. But we don't want this part because we want it to cool faster. So the faster way is to put the mug in a water bath. The second way to cool down hot tea is by using 2 cups. My original cup here with my hot tea, and I have an empty cup here. And what I will do is pour the tea into this cup and then pour it back into this cup. Back and forth. Back and forth. We're going to pour the tea back and forth between these 2 cups. So this one here is pour tea back and forth between the 2 mugs or 2 cups. Okay, and what would this do? Why would we want to do that? Transfer this heat back and forth. Well, we would want to increase the loss of heat from tea to air. Okay, so why we do this is to increase the loss of heat from our tea to the air. Alright, so these are 2 scenarios that we could use to cool your tea. And at CXC level physics or integrated science, these are the types of questions they would bring to make you think about real life situations where you could apply what you know about the transfer of heat. Now question 7. On a hot summer day, would you feel cooler if you stood under a ceiling fan, and why? So I have my ceiling here and my ceiling fan. Okay, so this is my ceiling fan with all its blades. And here's me standing under the fan. And it's a hot day. So the day itself is hot. Let's say the air in the room is at 30 degrees Celsius. So it's a hot summer day, right? 30 degrees Celsius. Would you feel cooler if you stood under the ceiling fan? And why? Now, fans, even if it was one of these standing fans, so let me try to draw a standing fan here for you, and you are standing in front of it, what fans do, they don't magically cool something. What they do is move air, and this movement of the air increases the rate of transfer between the object that they are blowing on and the air that they are blowing. So this fan here, what it does is pull this hot air onto you, but it also blows that heat from you away. So if you are sweating, it would increase the rate of evaporation of your sweat from your skin and you feel cooler. Okay, so those extra notes that popped up on your screen there, you need to take them down. Okay, write it on this paper somewhere because it's very important, and you will have questions popping up in your assignments or in future in your NCSE exam or any other end of term exam. Alright, asking you to explain these scenarios. So fans do not magically cool something. All they do is move air and increase the rate of transfer between the object they are blowing on and the air they are blowing. And it also increases the rate of evaporation of sweat from your skin and you feel cooler. So in this scenario, if the air is cool, so it's pulling cool air, which is maybe 22 degrees Celsius, and I am feeling warm at 37 degrees Celsius, the fan will pull the cool air, blow that cool air on you, and your heat will flow away from you, and your sweat will evaporate and move away into the atmosphere. So this is what fans do. So now let's look at some temperature scales. And the instrument we use to measure temperature is called a thermometer. Now there are different types of thermometers, and they each have their own application and special places where they are used. So I'm going to label these thermometers, and we will talk about what type of thermometers they are and briefly chat about how they operate. Now at this level, you're not expected to learn off the names of these thermometers or how they operate in detail. But later on, in Form 4, we will need to focus on a few of these thermometers and look at them in detail and know how to use them. So thermometers 1 and 7 are what we call liquid in glass thermometers. This is where the liquid expands or shrinks with temperature change. Thermometer number 4 is something called a manometric thermometer, and this determines temperature based on changes in gas or liquid. Thermometers 2 and 8 are called gas thermometers, and these are filled with gas, which expand or shrinks depending on the temperature. Thermometer 9 is a bimetallic thermometer, and this works with two metal strips. So bimetallic thermometers is something that we will focus on in greater detail in Form 4. Thermometers 6 and 10 are infrared thermometers, and these measure the thermal radiation of a body or object. Thermometers 3 and 5 are digital thermometers, and number 5 especially is a clinical thermometer. So again, in Form 4 we will go into detail about clinical thermometers, bimetallic thermometers, and liquid and glass thermometers. Okay, so these are the types of thermometers and a brief description of how they work, how they measure this temperature. Now on page 4 we will look at the units of temperature and converting from one unit to a next. There are 3 units of temperature. However, throughout this subject, as well as in physics later on, we will only be using degrees Celsius and degree Kelvin. Degree Fahrenheit would not be used, but it's still good to know because some thermometers that you find being sold in our pharmacies here do carry a reading of Fahrenheit. So these here are your symbols for degree Celsius and degree Kelvin, or sometimes just kelvins. We also need to know how to convert from degrees Celsius to Kelvin and back. Now, in Form 1, you would have learned about SI quantities and SI units. The SI unit of temperature, which is one of the base quantities, is the base unit Kelvin. Okay. Now let's look at how we convert from degrees Celsius to Kelvin and from Kelvin to degrees Celsius. So here we have 2 thermometers. One here is on one side of the thermometer. We have a scale, and this scale is in kelvins. We could see that it starts at 0 at the bottom, something called absolute 0. Here we have the freezing point of water in kelvins, and here we have the boiling point of water in kelvins. On the other side of the same thermometer, we have a degrees Celsius scale. Now, this type of thermometer is a liquid in glass. So here we have a liquid in glass that we could see, and as the temperature increases, the liquid will expand, the temperature will go up, the liquid will move up the tube. As it gets colder, the liquid would shrink and the liquid will move down the tube. Okay, so this is how this works. Now here you see absolute 0 for the degrees Celsius scale is minus 273 degrees. The freezing point of water here is 0 degrees Celsius. and the boiling point of water is 100 degrees Celsius. Now these temperatures here are important to know, these two especially. Now the next thermometer here has degrees Fahrenheit on one side, which we don't need to really know, and on the other side is degrees Celsius again. So when you are choosing a thermometer, be sure that you know if it's measuring in Fahrenheit or degrees Celsius. You would rarely find a thermometer being sold locally in kelvins. You would find it in Fahrenheit or degrees Celsius. Now temperatures that are much colder than the freezing point of water can exist. On the Kelvin scale, we call the equivalent temperature of 0 degrees Celsius or minus 273 degrees Celsius. So here, that's on this scale, right? So it's 0 kelvins or minus 273 degrees Celsius. The divisions on the two scales are equal. Okay, now if you look at the markings, it's exactly 273.15 and exactly 0 degrees at the same mark on the same thermometer. So 1 Kelvin is equal to 1 degree Celsius. To convert from a Celsius temperature to a Kelvin temperature, we add 273 degrees to the Celsius temperature. 0 degrees Celsius, if we add 273 to it, we will get the temperature of kelvins, which is the same thing, 273. Now we are seeing 273.15 here, but throughout the syllabus, we are to use just 273. To convert from a Kelvin temperature to a Celsius temperature, we subtract 273 degrees. So let's look here. Let's take absolute 0 kelvins. To turn this into degrees Celsius, we are to subtract 273, and we will get minus 273 degrees Celsius. You should be familiar with working with positive numbers and negative numbers from Form 1 Maths when you did directed numbers. So that's a topic you need to go to revise in math. Revise directed numbers. Okay? And this will help you understand we need to use this negative symbol in front of the number here. And we can have negative temperatures. Now let's convert some of these temperatures here into Kelvin and from Kelvin into degrees Celsius. To change 50 degrees Celsius to kelvins, we add 273. And this will give me 323. Now I don't need to write kelvins here again because our table has the units up here. Okay? Students make the mistake of writing that Kelvin, the units, back in the table. We don't need to, and you shouldn't. Okay? The units should be in your headings here of your table. Now, to change this Kelvin into degrees Celsius, we would take that value of degrees Celsius and subtract 273. And this will give me 192 degrees Celsius. Now in this case here, we have 35 kelvins and we want to subtract 273. So with the directed numbers, we subtract as normal. So that means 273 minus 35 will give me 238. And we keep the sign of the larger number. Okay, so 35 minus 273 is equal to 238. Now we are changing 95 degrees to kelvins, and to do that the rule says to add 273, and here we will get 368 kelvins. Now after you pause your videos and take down all your notes and you revise, you could practice converting temperatures to and from kelvins in lesson 1, activity 1. There's also some other questions based on what we learned from the start of this lesson there for you in that activity as well. So when you finish that activity, come back and we will look at some information that you would have learned in your lesson for states of matter, and we will look at some simulations and scenarios and some graphs for changes between states of matter. So you learned about change of state when we did the topic states of matter. Now, a change of phase is also called a change of state. So in this lesson and in future lessons, you will be hearing about change of phase. Some of these processes where there's a change of state is one, for example, melting, which is the phase change from solid to liquid. Freezing is the phase change from liquid to solid. Boiling is a phase change from liquid to gas. And condensation is the phase change from gas to liquid. So a change of phase is always a process where there is a change from one state to the other. You would have learned about sublimation. And this is the phase change from solid straight to a gas. So we skip the liquid state. And then the opposite of sublimation is deposition or desublimation. So deposition or desublimation is where we go from gas straight to a solid, and again we skip the liquid state. In this topic, we will be looking at what happens during those phase changes, these four here, in terms of the temperature changes and when heat is added or removed. So we wouldn't be focusing on sublimation or deposition or desublimation, okay? Just these four here we're going to be focusing on. Let's look at the simulation for phase change of ice at 10 degrees Celsius to water vapor, gas, at 150 degrees Celsius. The mass of the ice to be used will be fixed or constant. So this means we're using the same mass of ice. Okay, we're not adding any more ice during the process. We're not taking away any ice, okay, during the experiment. We're using the same mass of ice throughout the experiment. So this simulation that we are about to look at, you can find a link to it in the classroom. You can experiment with it on your own. So here's our simulation, and we are going to be looking at solid ice at minus 50 degrees Celsius. So it's colder than the freezing point or melting point of ice, right? And we're going to look at what happens when it moves from a solid to a liquid. This here is our graph. You will need to plot one of these graphs after we do the lab. So there are three things we need to look at: the position on the graph, the state, if it's still a solid or when it's a liquid or when there is liquid and ice in there, and the temperature. Alright, so we will be seeing the temperature increasing, we will be seeing the ice melting, and we will need to look at the graph as well. Okay, so I will pause in between and we will explain as it goes along. So let's start. We are starting at minus 50 degrees Celsius. So on your graph here, let me zoom a little bit. So on your graph here, we will be seeing the experiment starting from here, this minus 50 degrees here. And here on our y-axis, we have temperature in degrees Celsius. And on our x-axis, we have heat. Okay, so now heat is being added, but we are not changing the amount of heat we are giving the ice. This 10, this 20, this 30, and so on is actually time that is being passed. The heat will stay constant. So I'm going to start. Alright, so do you see here? I'm at minus 45 degrees Celsius, and here is solid. So on the graph, you see we are increasing. Our temperature as well as increasing. Our solid is still solid. Okay, so I paused it at 0 degrees Celsius. Right, some good reflexes there, right? So we now start the melting process. Okay, so here we still have solid ice at 0 degrees Celsius. Now let's take a look at what happens here. The temperature is still 0 degrees, but look at what is happening here. The ice is melting. Look at the graph. There's no temperature increase. It's on this flat line here as we plot the temperature against time. Okay? So look, we are still at 0 degrees Celsius. Alright? And we are at 6 degrees Celsius here. We still have a little piece of ice. We have a liquid. And look at where the graph is. Right? So we are at the bottom here of this incline. Right? And we are at the end of this flat line here. Seven degrees. Temperature is increasing. We are going up this incline here. Now we are at liquid only. Alright, 32 degrees. We're going past room temperature. We are increasing again. And here we stop at 50 degrees. Okay, so we know for sure that here we have our liquid state at 50 degrees Celsius. Okay. Now let's go from liquid to gas. Alright, so now we put our cup on a stove. This looks like an electric stove. Please do not try this experiment at home. This cup will either shatter or melt if it's plastic. Okay, so we're gonna start with our liquid at 50 degrees Celsius. Notice the molecules. They are moving a little bit. They are spaced out but not too far apart. And we are going to heat now and look at it turn into a gas. So here we have our liquid being heated. Its temperature is rising. Now you may see one or two little water molecules escaping. Alright, evaporation is happening here. What happens with evaporation? Right, so I stopped it at this point here, is that some of the molecules closer to the bottom of this glass here would have enough energy to escape as a gas, but not the entire volume of liquid as yet. So we're at 90 degrees Celsius. Okay, so we're heating. Now we're at 100 degrees Celsius. Okay, and we are at the beginning of this flat line here and at the end of the incline, and we call here what's happening here vaporization. Okay, so let's continue. It's still at 100 degrees Celsius. We have water vapor, we have water molecules escaping. It's actually boiling here. Okay, the volume, look at the level of the water, it's decreasing, so we're actually losing some amount of water here. Right, it's still boiling. Okay, so now we are at the end. We are at the end of this flat line here, and now we are going to increase temperature. What are we increasing this temperature of? We're almost out of water. Right, what we're heating here now is the water vapor around it. Okay, so we have the gas at 120 plus and increasing. Right, so we have an increase in temperature again. Alright, and the simulation will stop at 150 degrees. Now we are at gas. So this here is a general shape of any substance starting from solid phase to a liquid to a gas. Okay, this is a general shape for any substance. Okay, but for water in particular, we have special temperatures that we need to have on our graph. And those main temperatures are where these flat lines occur. Zoom in. Where these flat lines occur. One is 0 degrees Celsius. That's our melting point of ice. And this one here at 100 degrees Celsius, which is the boiling point of water. So let's go back to our page 5. And try to draw our own graph and put in all the information and all the details of what is happening at each point on this graph. So now let's put in the details on this heating curve of water or graph of temperature in degrees Celsius against time in minutes of water. Okay, so our y-axis is our temperature and our unit is degrees Celsius. Our x-axis is time in minutes. And there's another thing on the x-axis. Heat. Heat is added. Now the heat will be constant throughout the entire experiment, okay? We wouldn't have medium heat at the beginning and then increase the level of the heat at the end. No, the heat is constant. Now we need to put in our important temperatures on this graph. So we are starting with ice at minus 10 degrees Celsius. So minus 10 degrees Celsius would be here. And we don't put in the units on our axes because we already labeled it here. This point here will be our 0 degrees Celsius. Okay, this would be the point at which the ice will start to melt. Our next important point is our boiling point, and that happens at 100 degrees Celsius. And then we are heating the water to 150 degrees Celsius. So that's our final temperature. Now this is a sketch. We are not drawing this to scale. However, we still need to put in our temperatures in a proper order. So we wouldn't want this minus 10 to be up here on our y-axis. Anything below 0 is negative. So let's draw in our curve. That would be the curve that we saw in the simulation. So I'm going to use yellow to draw in the curve. I'm starting at ice at minus 10 degrees Celsius. So I'm starting here. So I'm going to increase. So we're adding heat over time, and as time passes, the temperature of the ice is going to increase until it reaches this point here at 0 degrees Celsius. And then we saw at 0 degrees Celsius, we saw a flat line like this. And it stayed at 0 degrees Celsius for a while. And then what happened here? We saw the ice melting and becoming liquid. And then after a while, we saw the temperature increased again all the way to 100 degrees Celsius. And what happened there? It stayed for a while at 100 degrees Celsius. And then lastly, the temperature increased again all the way to 150 degrees. So this is the general shape of the graph that we want to have when we are heating a substance from solid to liquid to gas, or from the liquid state to gas. Now, let's put in the other important processes here. I'm going to label this point here on the graph E, this point here B, this one C, D, E, and the top here F. And we are going to write about what is happening between each of these points on the graph. So first let's start with here, this part here. During this stage from minus 10 degrees to 0 degrees, what did we have? We had a solid. We had solid ice only. And our particles of our solid ice were closely together. But remember, this is water. And we spoke about water being an exception. Solid water expands. Okay? So it's not too tightly packed together. There's spaces in between. But it's still a solid. Here, what happened here? When the temperature was at 0 degrees Celsius and there was no temperature increase, we had solid turning into liquid. And then what were we heating after? After we turned all the solid into liquid. When it was increasing, when the temperature was increasing, we had liquid only. Alright, so we have liquid only between C and D. Then, we saw when we reached 100 degrees Celsius, it stayed for a while at 100 degrees Celsius. And what was happening here? We saw the liquid turning into gas. So we had two states here at the same time. And then after the 100 degrees and we're heating again, we had gas only. Now, the name of this phase change here between B and C is called melting. For a heating curve, okay? Melting. This process here is melting. And between D and E, this process here is boiling. Or sometimes it could be evaporation. Alright? But more so boiling. Okay? Now when you're putting in your notes on this graph, I would like for you to put in as much of the details as you could here. If not, you could always write it below here. Okay, so here at C to D we have liquid only. Alright, liquid only. In boiling we have the liquid becoming gas, and in gas we have the particles far away from each other, right? And in E to F we have gas molecules only, very far apart. Alright, so you would need to pause this video and take down your extra notes of what was happening at A, B, B, C, C, D, D, E, and E, F. Okay, and all these notes on your graph, and draw this graph here as well. Okay, now your lab would be a similar graph to plot like this. So when you finish taking this down, we will look at the cooling curve of water next. We will look at the simulation, what is happening, and then we will do our own graph like this and put in the information. Okay, so now let's look at a simulation for the phase change of water vapor, which is a gas, at 150 degrees Celsius down to ice at 10 degrees Celsius. But first we'll look at moving from gas to a liquid, and then we'll look at the liquid to a solid. Alright, so right now I am at solid. So my starting state is going to be gas. Alright, now notice the gas molecules of water, how fast they are moving. They have high kinetic energy. Okay, they're filled with all this thermal energy, and they're bouncing around in the glass. Now we're going to move from gas to liquid. So again, we're going to keep our eye on the graph. We'll be starting at here at 150 degrees Celsius to keep an eye on the temperature and keep an eye at what is going on inside of this glass. So I'm going to click start, and we're seeing here the temperature is decreasing. We are going down the graph, and we are at 100 degrees Celsius. Okay, so at 100 degrees Celsius we started this flat line here. Now in our last graph, when it was going in the opposite direction, when we were adding heat, we were vaporizing or boiling. Now that we are removing heat from the system, we are condensing. You could see here on this flat line we have water being formed already at the bottom of the glass. And in the lab that we will be looking at, we need to look at the same things, the temperature and what state is in the glass at that time. So let's continue. So we are seeing no temperature change here, right? We are at the same temperature, 100 degrees Celsius. And look, we have liquid and gas at the same time. And we are dropping now, we are decreasing our temperature. Alright, we dropped from 100 to 50. And we are at liquid. Okay, no more gas in there. So this is what our liquid molecules look like. Now we're going to look at changing from this liquid to a solid. So my starting state is a liquid now, and we're going to change this into a solid. So the atmosphere change here. We're in a freezer maybe, okay, and we're going to remove heat to change this from the liquid state to the solid state. So we're starting at 50 degrees water in a freezer, here we started, and our temperature is decreasing. Right, the molecules start to move slower. All right, notice how the molecules are moving. All right, 0 degrees Celsius. Look at what is happening in this glass. And on the graph, freezing has started. Okay, and our previous graph, this was melting. So the freezing point and the melting point is the same thing. The boiling point and the point at which we condense is the same value of 100 degrees here, and the freezing and melting point is 0 degrees Celsius. Okay, look at our bonds being formed here. So on this flat line here, we have bonds being formed. Okay, these black lines between the molecules weren't there before. So let's continue. All right, look at the glass. And we have solid ice. And we are at the end of the straight line here. 0 degrees Celsius, freezing, and we have solid ice there. All right, now notice the molecules in the glass. Water is an exception to any solid. They don't tightly pack close together. They do have some spaces in between them because water expands. If water did not expand, then when a pond freezes over, fish and all life inside of the pond water would not be able to survive, because then the entire pond will freeze over. We know the ice floats on top of the water, so fish could still live underneath. This is why we draw water molecules a little different to any other solid. Okay, and we went through that simulation for states of matter, where we looked at the differences between the other solids and what solid water looks like. So let's continue. Let's cool this down to below 0 degrees Celsius. Okay, very little vibration there. Okay, and we are cooling it all the way down, and we stopped at -50 degrees. Okay, so very little vibration. They're only allowed to move within that little spot that they have there. So now we are going to look at the graph, the blank graph on page 6, and we're going to fill in some of the things that we see happen here. Now again, this simulation is in the classroom. You could take it and practice, look at what is happening, right? Play around with it. If you want to learn some more, okay, we have, if you click on concepts on the top screen here, at the top of your screen, you see concepts. So you click on these, any one of these here, and you will get notes, right? You have notes here, you read that, you have a video to look at, and a real world application. Okay, if you click on the phase diagrams, right, phase diagram, 6 videos for you to look at. Now some of these might be a little too high level for you, but knowledge will never go to waste. Phase diagram for water, you go ahead and read that, and real world applications. Okay, change of state, I think this was in your classroom already for you to learn, so you could go ahead and read up those. Challenge me here, okay, is some questions that require you to think. So you could go ahead and try these on top here and explore this site. So here we are on page 6, and we're going to draw the cooling curve of water, or the graph of temperature against time in minutes of water. Okay, so you could write your title of your graph in 2 ways. We could write it graph of temperature against time for water, or the cooling curve of water. Now this here is the more popular way to describe this graph. Okay, so we're going to start at water vapor at 150 degrees and go to ice at 10 degrees Celsius. Now because it's water, we have again our important points, our 0 degrees, our 100 degrees Celsius, and this here depends on what the question gives you. So here is 150 degrees, and we're going to -10 degrees Celsius. Okay, we need our labels: temperature in degrees Celsius, this is a bracket here, and our time in minutes. Okay, so here we're using time in minutes and not seconds, because these changes don't occur in seconds. They take some time. And also heat is being what? Over time heat is being, now this is cooling curve, so heat is being removed, okay, not added. So be careful if the question wants you to draw a cooling curve or if it wants you to draw a heating curve. So we are starting at, where would we start? We would start here. Okay, we are cooling the gas from 150 degrees. So we will be decreasing the temperature all the way down to 100 degrees. And here at 100 degrees Celsius, we know that there's a phase change. Okay, a change of phase from gas to liquid. And then we would cool again all the way down to 0 degrees Celsius. And then here another phase change will happen. Okay, from liquid to solid. And then we will cool the solid a little more all the way down to minus 10 degrees. Okay, so if we look at the previous graph, it's opposite. Okay, we started here and we went up. And in this one, for the coolant curve, we're starting at a high temperature and we're decreasing. So now let's write in our important points. So I'm going to label. I'm going to start here. This is my A, B, C, D, E, and F. Okay, and we're going to be writing what is happening between these stages and at these stages. So here between A and B we have gas only. Okay, so the gas molecules will be spaced out, high kinetic energy. Alright, and here we're seeing a decrease in temperature, so you could write that in. So at A, C we have gas only, we have a decrease in temperature. Sorry, this is AB. Okay, AB, decrease in temperature, so high kinetic energy, heat is removed. Okay, and while the molecules have high vibration, at BC we have a phase change from gas to liquid. And recall here, what did we see on our simulation? What was here called? Condensation. Okay, condensation was happening here. And here we are taking the gas molecules spread far apart and we're bringing it back a little closer together to form liquid water molecules. And here is gas and liquid at the same time at BC. Now at CD we have liquid only, and our liquid molecules, and here we are decreasing temperature again. For BC we had no temperature change. This is the most important part of this graph. Okay, no temperature change. So at CD now we have decreasing temperature and heat being removed. Now pay close attention to what is happening at these phase changes. So the phase change is what we want to focus on. Here, what do you think is happening to the heat that is being removed here? What is happening to this energy? Well, the energy here is being used to form bonds. So at BC, bonds are formed. Okay, so we go in closer from gas to liquid. And DE here is another phase change. So DE is another phase change from liquid to solid. So here we have both liquid and solid states, and we have no temperature change, right? Because bonds are being formed. And we saw in the simulation what the bonds look like, right? They were the black lines between the water molecules. So here's what that looked like. And then at E and F, what we have happening here, we have solid only. Okay, so E and F, we have no phase change, but we have solid only. Now we talk about here being condensation, but at this phase change here, what is that process called? That process is freezing. And freezing occurs at 0 degrees Celsius. The 100 degrees Celsius point and the 0 degrees Celsius point are two values that must be on your graph. If you don't have those two values when you have to draw this type of graph or this sketch, you're going to lose marks. Because we know water boils at 100 degrees Celsius or very close to it. It depends on if your water is pure water or if it has impurities in it. And it freezes at 0 degrees Celsius. So pause and take down your notes. I think you would have enough space at the bottom of the page to write. And then we will merge both graphs, the cooling curve and the heating curve, on page 7 on this graph here. Questions that you will get will most likely look like this graph. So do you notice there is no negative value here? We start directly at 0 degrees Celsius. So the lab that we will be looking at will start at ice at 0 degrees Celsius. So on the same graph below, we're going to show both the heating and cooling curve information from ice at 0 degrees Celsius water to water vapor at 120 degrees Celsius. And water vapor at 120 degrees Celsius to ice at 0 degrees Celsius. So the first things you want to do is label your axes. Temperature in degrees Celsius, time in minutes. We want to put in our important points, our 0 degrees Celsius, our freezing point. We want to put in our 100 degrees Celsius here, and any other values that they give you in the question. So they gave you 120 degrees Celsius, right? And if you use your ruler and you go across, please use a ruler, right? That should be a point there. Your 100 degrees should be that point there, and your 0 degrees here. Okay, so make sure when you're drawing them, they line up to what temperature it's supposed to be. Right, so we could put in what states we have here. At this state here, we have both solid ice and liquid. At this stage here, we have liquid only. Here we have liquid and gas. Here we have gas only. And let's put in the processes that happen at phase change. So here is a phase change. And here's a phase change as well. And let's give the names of the processes. So here we have freezing or melting. Okay, both points are the same, 0 degrees Celsius, right? So freezing and melting happens at 0 degrees Celsius here, and we have a phase change. At 100 degrees Celsius, we have condensation, or we have boiling or evaporation. Okay, and boiling is the more popular one. Now there are some words that we need to know, and one more step to this. At the phase change, there is something called latent heat or latent energy. Okay, so latent heat, and this one here, from where we have solid going to liquid, we call this the latent heat of fusion. And here, our phase change, we call this phase change the latent heat of vaporization. Okay, latent heat of vaporization. Now, for your lab, you would need to identify where your phase change occurs on your graph and label your latent heat of vaporization. So you could either write it on the graph itself, or you could label A, B, C, D and identify in your discussion where your latent heat of vaporization is and where your latent heat of fusion is. So now let's talk about what is this latent heat of fusion and what is this latent heat of vaporization. So one thing to note with all these change of state is that no matter what state or what process is happening here, water remained water. Okay, so during a change of state, the chemical composition of the substance stays the same. Water will still be water at any part of this process. Okay, it will just be either frozen water, liquid water, or gaseous water. Okay, so that's important to note. We wouldn't start with solid ice and end up with liquid gold, right? Water will stay water right through. Okay, so be sure to add this note to your notes as well. Okay, this is very important. So let's take a closer look at what this latent heat of fusion and latent heat of vaporization is. So in areas where phase change occurred, which was the conversion of solid to liquid or liquid to solid or liquid to gas and gas to liquid, we have these flat portions of the graph, and we call those latent heat of fusion, or on the next page we will talk about latent heat of vaporization. So let's first look at the solid and liquid. Let's first look at the solid converting into the liquid and the liquid changing into solid. So the word latent means hidden. And we could see here on the graph, although we are supplying heat, there is no change in temperature. So it's almost as if this heat doesn't exist. We know that we are supplying heat to the system. But as we said before, the heat is being used to break the bonds from a solid to form a liquid. That's why there is no temperature increase. So when we change from a solid to a liquid, or a liquid to a solid, that heat energy is called the latent heat of fusion. And we use a capital L as a symbol for latent heat of fusion. And that latent heat of fusion for a solid is the heat energy required to change it from a solid to a liquid without any temperature change. So the heat absorbed to cause the solid to melt to the liquid is called the latent heat of fusion. So this here is the general definition of what the latent heat of fusion is. Now, each substance has a different value for the energy required to change it from a solid to a liquid. That heat energy is called their specific latent heat of fusion, and we use the letter L, so the common letter L and a subscript of F. So the specific latent heat of fusion for ice, which is solid water, would be different to the specific latent heat of fusion for gold. You would need to supply more heat energy to melt solid gold to liquid gold than you would need to melt ice to liquid water. So this is what the specific latent heat of fusion is. And this definition here is something you would need to learn. The specific latent heat of fusion of a solid substance is the heat energy required to change 1 kilogram of it from solid to liquid without any temperature change. And this topic that you're learning now, if you are doing physics in Form 4, this is one of the founding lessons for thermal energy again. Okay, so thermal energy here that we are doing at this level are just part of the entire topic. Thermal energy is a very big topic. So there will be other lessons if you choose to do physics for Form 4 and Form 5. Okay? Now, there's a formula to find the specific latent heat of fusion. That formula is the heat energy supplied divided by the mass of the substance. And these are the symbols we use. So here we have common L subscript F is equal to E, which represents the heat energy, and this little h subscript h just shows that this energy is due to heat. Later on you will learn about different types of energy. So we use this h here to show that this is energy due to heat. And the M is for mass. So this formula you would need to learn as well. Now the units for the specific latent heat of fusion is joule or joules per kilogram. And those are the units because the unit for energy is joules, and we are dividing joules by mass, and the unit for mass is kilogram. So we could write it like this, or we write it joules per kilogram. The specific latent heat of fusion for ice is this value here, 340,000 joules, or if we change it to the scientific form or scientific notation, it's 3.4 by 10 to the power of 5 joules. Or if we convert it to kilojoules by dividing by 1,000, it's 340 kilojoules. Okay, so these are the ways we could express these large values, and converting large numbers to scientific form or scientific notation, okay, or standard form, is a lesson that you should have done in Form 1. Okay, now if we rearrange this formula here and we wanted to find the heat energy instead, we would take the heat energy. So this here is heat energy is equal to mass multiplied by, and the L subscript F is the specific latent heat of fusion. Now this value here, you are not required to learn off this value. If you are given a calculation question, they will give you this value. So let's take a look at some examples using these formula. So on page 8 we have some questions here. So let's look at example 1. 1 kilogram of copper and 1 kilogram of nickel. So 1 kilogram here is the mass of these substances, right? The mass are both heated continuously at the same rate. Determine which metal will completely melt first. Use a value of 205 kilojoules per kilogram for the specific latent heat of fusion of copper, and use a value of 297 kilojoules per kilogram for the specific latent heat of fusion of nickel. Okay, now we're talking about latent heat of fusion, so we know that we are moving from solid to liquid. All right, there is no temperature change at this point, and for copper, the specific latent heat of fusion is 205 kilojoules per kilogram. And for nickel, the specific latent heat of fusion is 297 kilojoules per kilogram. Now the mass is the same, okay? We're using the same amount of copper and the same amount of nickel. Now the mass is the same. 1 kilogram of feathers is equal to 1 kilogram of flour. Okay, 1 kilogram of whatever it is, no matter what it is the same amount. Okay, so just keep that in mind. Now we want to know which one is going to melt first. Now how much energy does it take to melt? Now do you remember what your definition is for specific latent heat of fusion? Let's go back. The specific latent heat of fusion of a solid is the heat energy required to change 1 kilogram of it from solid to liquid without any temperature change. So basically, what this is saying is that this is the amount of heat energy we need to melt 1 kilogram of solid. Okay, so here we are using 205 kilojoules to melt copper. We are using 297 kilojoules to melt nickel. So which one would melt first? The one that uses less heat, right? So when we reach a value of 205 kilojoules, copper will start to melt first. When we reach 297 kilojoules, then nickel will start to melt. So a real-life application of this would be, for example, if we wanted to make a pot and the pot would be exposed to heat energy of, say, 260 kilojoules per kilogram. Which material would we choose to make that pot out of? Now, we wouldn't choose copper because copper would melt before we even reach this 260 kilojoules per kilogram. We would want to make the pot out of nickel because even though we reach this temperature, it wouldn't melt, because to melt nickel we need 297 kilojoules. Okay, so this is a real-life engineering application of why we learn this topic. So let's look at question 2. 30 grams of molten gold is allowed to solidify. It releases 1890 joules of energy to the surrounding environment as it does so. What is the specific latent heat of fusion for gold? From page 7, we know the formula to find specific latent heat of fusion is the heat energy divided by the mass of whatever solid we're using. And we know we're using latent heat of fusion, so we know we're going from solid to liquid. On page 7, we also said the units is joules per kilogram, okay, which means we're dividing the heat energy by kilogram. Now, this kilogram is important here. It means that we cannot, in our calculation, use grams. We must use kilograms. So we are going to convert this 30 grams into kilograms. 1000 grams is equal to 1 kilogram. 30 grams will be 30 divided by 1000, which is 0.03 kilograms. We move the point 2 places to the left. Now, the latent heat of fusion is equal to the heat energy, and they gave us that heat energy is 1890, and we're going to divide that by the mass, 0.03. You wouldn't need a calculator for these things, okay? The calculations would be simple. Dividing by a decimal, we move the point such that we get a whole number as our divisor, and the number of places we move this point, we do the same thing here. So if I move this point 2 places, it means I am adding 2 zeros here. So I'm really dividing 189,000 divided by 3. And again, you don't need any calculators here. 18 can be divided by 3 6 times. 3 could go into 9 3 times. And the rest are zeros. Okay? And your units is joules per kilogram. And if you wanted to put it in kilojoules, you would divide by 1000 and you would have 63 kilojoules per kilogram. Number 3. A metal at the temperature at which it melts is heated until all the metal has become liquid. It takes 41 kilojoules to completely melt the metal, and its mass is 0.2 kilograms. What is the specific latent heat of fusion of the metal? So we're talking about fusion again, so we're going from solid to liquid, and we want to find the specific latent heat. So they gave us the heat energy, which was 41 kilojoules, which is 41, and kilo means 1000, right? Joules. And we have our mass. Our mass they gave us already is in kilograms, so we don't need to change that. Now the formula on page 7 for latent heat of fusion is the heat energy divided by mass. So that is 41,000 divided by the mass they gave us is 0.2. We're going to move this point one place to make the divisor a whole number, which is 2. And then we'll move this point here one place. So it's an extra 0 we're adding there. So let's rewrite that. 41. Now it becomes 410,000 divided by 2. And no calculators again. 2 could go into 4 2 times. 2 cannot go into 1, so we put a 0, but 2 could go into 10, so we put a 5 there, and we have 3 zeros, okay? 0 divided by 2 is 0. So here we have the specific latent heat of fusion of the metal in joules per kilogram, or if you wanted to put it into kilojoules per kilogram, we divide this by 1,000. And we will get 205 kilojoules per kilogram. Determine how much energy is needed to melt 2 kilograms of ice. And we want to use a value of 334 kilojoules per kilogram for the specific latent heat of fusion of ice. So they gave us LF, which is 334 kilojoules per kilogram. M, they already gave us mass in kilograms already. So on page 7, the formula to find the heat energy was mass multiplied by the specific latent heat of fusion. 334 multiplied by 2. And don't forget this part here. It is kilojoules per kilogram. Okay? And that's it for calculations for specific latent heat of fusion. Now on page 9, we would look at the specific latent heat of vaporization. The formula is the same, but the specific latent heat of, and this here should be vaporization. I would have fixed that in your copy, so your copy should have had vaporization here, right? Is different to the specific latent heat of fusion for ice, right? So it's the same formula, okay, in both cases, except we have to make sure that we are using the correct value here when we are changing 1 kilogram of a liquid to a vapor. And the calculations are the same, okay? So all the calculations that we did on page 8 will be the same way we would do it for the specific latent heat of vaporization. A pan of water reaches 100 degrees Celsius, but the pan is still left on the heat. So eventually all of the water turns into water vapor. So our process here, our change of phase is liquid to gas, okay? So for vaporization, it's a change from liquid to gas. Calculate the energy needed to evaporate 1.2 kilograms of water contained by the pan, and use a value of 2258 kilojoules per Kelvin for the specific latent heat of vaporization. So the same formulas we're going to use. They gave us a mass and they gave us it in kilograms already. Now this is L subscript V for vaporization, okay? 2258 kilojoules per kilogram. And the same formula, we're going to use heat energy is equal to mass by the specific latent heat, and in this case it's vaporization, not fusion. And 1.2 by 2258. When we multiply in, so primary level multiplication here by decimals, we multiply, we don't need a calculator, we multiply without the decimal place, okay, and the answer that we get, we put back one decimal place here because of that there, right? So our answer is 2709.66 watt kilojoules. Okay, and that's our answer here. 2709.6 kilojoules, and it's the same calculations as we would do on page 8. The only difference is we are using the specific latent heat of vaporization, and you would need to know when to use the fusion and when to use latent heat of vaporization. So after you revise this topic, you can feel free to try activity 2. And the next lesson, we would look at a lab, and we would write up a complete lab for the heating curve of water. So pay close attention to the graph on page 7. The graph that you would need to plot for the lab will look similar to that. So as soon as you complete activity 2 and you have a good score in that, we'll move on to the lab. On page 10, there is a little summary chart given the differences between heat, temperature, and thermal energy. So this is just for you to learn and to remember. Again, here, how is it expressed? We would not be using Fahrenheit in any of our calculations or notes, but it's just for you to have a general knowledge that yes, temperature is recorded in Fahrenheit as well. And that brings us to the end of lesson 1, and I'll see you in the video for the lab.